Every year, massive continent-spanning plumes of mineral dust are lifted from arid regions and swept into the sky. These particles remain aloft for thousands of miles, carried by global winds before eventually settling back to Earth. The problem is, despite the sheer volume of dust up there, it has been a highly unstable variable in global climate models. Scientists couldn't accurately predict whether a specific dust cloud would reflect sunlight to cool the planet or absorb it to warm the atmosphere. That dual nature is determined by the presence of one specific material, iron oxides. If a dust particle contains iron, it absorbs heat. If it lacks iron, it acts like a tiny mirror, deflecting radiation. For decades, scientists couldn't accurately calculate the atmospheric concentration of that iron. Without this variable, resulting climate projections were unreliable. To accurately project the future temperature of a warming Earth, scientists needed a way to lock down the contents of that dust. Measuring the mineral composition of the entire planet's dust required leaving the planet entirely. NASA developed an instrument called EMIT, the Earth Surface Mineral Dust Source Investigation, and installed it on the International Space Station. It functions as a chemical camera in orbit, using a technique called imaging spectroscopy. This gives the instrument extreme capabilities. It can scan vast, completely inaccessible desert regions and map the precise molecular makeup of the ground at a resolution of 60 meters. EMIT's primary target is hunting for the specific spectral signature of iron oxides hiding in the sand. The data from this instrument finally gave scientists the information needed to draw a precise mineral map of the Earth's dust sources. The map revealed significant geographic differences. North African dust is rich in iron, meaning it actively absorbs heat and contributes to warming. Conversely, Asian dust is highly reflective, creating an atmospheric cooling effect. To see exactly how much this mattered, researchers at Cornell University plugged this regional EMIT data into 4 independent global climate models. When models absorbed the exact iron oxide levels, uncertainty plummeted from 0.62 watts per square meter to just 0.1. Over the Sahara, the largest dust source, simulation errors dropped by 80%, matching satellite observations perfectly. By solving the iron equation, scientists have eliminated a major source of uncertainty in global climate science. Today, our understanding of dust's effect on solar radiation is backed by high-fidelity mathematical data, rather than educated guesswork. Because researchers no longer have to guess the chemical composition of the dust, they can pivot their focus to its behavior as it travels through the atmosphere. They can study exactly how these traveling minerals fall into the sea, fertilizing ocean ecosystems, or how they settle onto high-altitude snowcaps, darkening the surface and increasing heat absorption. They can even trace its role in the complex formation of atmospheric clouds over arid regions. By mapping the mineral makeup of the ground beneath our feet, we have provided the data needed to understand how the Earth's energy balance is shifting.